So again, permutations are when things are being selected and order matters. Over the last couple of classes, we've been arranging objects. We'll do more of that, but we'll introduce more restrictions and also work with sets of objects where there will be identical objects, repetition. So letters that repeat in a word would be one example, right? So in many problems, restrictions are placed on the order in which objects are arranged. In this type, we always deal with the restrictions first. So the first one, we want to know how many ways all the letters of the word oranges can be arranged. And if there's no constraints, there are 7 letters there. And so they could be arranged in 7 factorial ways. So this could be done also using the fundamental counting principle. Mark down 7 spaces. And there'd be 7 for the first letter, then 6, then 5, all the way down to 1, which you'd multiply together, and that's the same thing as 7 factorial. If the first letter must be the letter N, there's only one choice for the first letter, and there's 6 remaining letters to arrange, and they could be arranged in 6 factorial ways. So the answer is 1 times 6 factorial, or just 6 factorial. Which is 720. So this next one is different. What if the vowels must be together and in the order O first, A second, E last? So for this one, I'm going to mark down the 7 spaces. And the vowels must be together in that order. What we have there is we have only one possibility, though. They can take up the first 3 spaces, or they can take the second and third and fourth spaces, or they can take the third, fourth, and fifth spaces, and so on. So you could definitely do all those different possibilities, okay, with this being one possibility. And then you would have 4 letters left to be arranged, so they could be arranged in 4 factorial ways, okay? Then you would have to do that another 1, 2, 3, 4 times. And those 4 times would be shifting the letters over one spot. Okay, so you could do that. You'd get all those different possibilities and you'd add them up, because this would be an or scenario as well. You could have this possibility, or the next possibility was when the 3 letters are shifted one space over, or, and you keep doing that, okay? But there is an easier way, and here's what it would be. Because these items have to stay together, they actually will count as one object to be arranged. If one of them moves, the other 2 have to move with them and stay in that order. So they count as one object to be arranged. There are 4 other objects to be arranged as well. Those will be the remaining 4 letters. So now you actually have a total of 5 objects to arrange. These 3 that count as 1 plus the remaining 4. You have 5 objects that you're arranging, and they can be arranged in 5 factorial ways, which is 120. That's the answer to this. Now, part D, the vowels must be together, but in no particular order. So the only difference is you're going to have your 5 factorial ways that the 5 objects can be arranged, but then you're going to also multiply that by 3 factorial. And that 3 factorial represents the ways the 3 letters can be arranged amongst themselves. There are 3 objects you're arranging amongst themselves. That's where the 3 factorial comes in. So it'd be 5 factorial times 6, which is actually 6 factorial, or 720. Right? So we're going to see more examples where objects have to stay together, like this next one. 5 people, Shay, Reese, Caddis, Matthew, and Simone are seated on a bench, and how many ways can they be arranged if Matthew must be seated in the middle? So there are 5 people, and if Matthew must be seated in the middle, there's only one choice for the middle seat. We started with 5, now there's only 4. So you have 4 choices for the first seat, then 3. The middle seat is fixed, so there's only one choice there. and 2 times 1 for the last two spots. So essentially, it's 4 factorial. 4 times 3 times 2 times 1, which doesn't change anything. So that's 24. Now, what if Shay and Caddison must be seated together? So again, like the situation we had above with those letters, those vowels that must be together, Shay and Caddison will count as one object to be arranged. They have to stay together. So they count as one object to be arranged, plus the 3 remaining people gives us a total of 4 objects to arrange. So it's 4 factorial. However, we also multiply that by 2 factorial, which represents a number of ways that Shay and Caddison can be arranged together. Shay first, Caddison second, or Caddison first, Shay second. 2 factorial is just 2. So this will give us 48. 4 factorial is 24 times 2 factorial, 48. Now, C says, what if they cannot be seated together? There's going to be 2 different ways that we can do this. So here's solution 1. Will be a little bit easier to do. Solution 1 could be found by taking all possibilities and subtracting the possibilities with Shay and Caddison together. There are only 2 things that can happen here. Either they are together or they're not. Only 2 things that can happen. So if you take all the ways that they can be seated together and add all the ways that they cannot be seated together, that will equal all the different possibilities in this scenario when you have 5 people that you're arranging. Okay, so all possibilities would just be 5 factorial minus the possibilities with them together, which is what we found in part B, that's 48. 5 factorial, I think, is 120. Yep, so it's 120 minus 48, which is 72. So there's one way we can do this. Probably the easiest way to do it is by taking all possibilities and then subtract the possibilities with Shay and Caddison together, especially seeing how we already had the answer for that second part. But here's another way you can do this. They must not be seated together, meaning you can't have one beside the other. Okay? So what I'm going to do is I'm going to mark down 3 spaces. These spaces represent the other 3 people. Okay? These spaces represent the other 3 people. Shay and Caddison cannot sit together, so these other spaces represent Reese, Matthew, and Simone. I'm going to change colors now because these new spaces that I'm marking in there represent the seats that Shay and Caddison could be put in. Now, there are 4 spaces there, but we're only arranging 2. So you're only going to use 2 of these spaces, but this represents where those people could sit. Because if you put Shay in the first position, there's going to be someone else in the next position. So no matter where Caddison sits, it won't be beside Shay, and so on. Okay, so we've got 4 spaces first for Shay and Caddison. So there'll be 4 choices for where, let's say, Shay can sit, times 3 spaces where Caddison can sit. And it doesn't matter if you say you're going to put Caddison in first. There's 4 places where she could choose, and then 3 where Shay could choose. Times, now we're just going to arrange the remaining 3 people. That those can be arranged in 3 factorial ways. So the answer is 4 times 3, which is 12, times 3 factorial. 3 factorial is 6. 12 times 6, get the same answer, 72. right? So 2 different ways that can be done. Example 3, how many different 3-digit even numbers greater than 300 can be made using the digits 1, 2, 3, 4, 5, and 6, and no digits are repeated. So they're going to be 3-digit numbers. So let's mark down 3 spaces. And we have actually 2 different scenarios that we have to look at here. And here's the reason why. We have to have 3-digit numbers, but they have to be even and they have to be greater than 300. Okay? When you look at the even digits, that's a 2, a 4, or a 6. And the reason we're talking about those is because in order for a number to be even, this last digit has to be even. That's one of our restrictions, right? However, depending on what digit you put at the end, that's also going to affect the number of choices you have for the first digit. Okay? The first digit can be 2, 4, or 6. But if the last digit can be 2, 4, or 6. But if the last digit is a 4, then it can't be used for the first digit. And that's one of the numbers you could potentially use so that the number itself is greater than 300. Also, if the last digit is 6, then you can't use it for the first digit either. However, if the last digit is 2, it doesn't matter what the first digit is because the 2 can't be used for the first digit. So because depending on what digit you choose for the last position, it will affect the number of choices you have for the first position. We are going to have 2 different scenarios here. Okay? And so I said, well, it depends whether the last digit is a 2 or 4 or 6. That affects the first digit. We can also look at it a different way and say, depending on what the first digit is, it will affect the choices we have for the second digit. So that is true as well, and that's how I'm going to attack this. My first scenario is if the first digit is even. My second scenario will be if the first digit is odd. So if the first digit is even, remembering that the number itself has to be greater than 300, that means there's only 2 possibilities, the 4 or the 6. 2 possibilities there. Now let's go to the last digit, because that's another restriction, and we always deal with our restrictions first. If the first digit is even, we can't use that same digit for the last position. There are 3 even digits, a 2, 4, or 6, but I've already used one of them. So now there's only 2 choices for the last digit. We started with 6 digits, we've used 2, that leaves 4 for the middle digit. So 2 times 4 is 8, times 2 is 16. Again, remember the word or means to add. Now, what if the first digit is odd? Again, the digit must be greater than 300, so the first digit cannot be a 1. It can be a 3 or a 5, so there's 2 choices for there. But now we'll have all 3 even digits available for the last place. We haven't used 1 yet. In order for the 3-digit number to be even, the last digit must be even, and we haven't used 1 yet. And once again, you'll have 4 choices for that middle digit. So now it's going to be 2 times 4 times 3. 8 times 3 is 24. So we're going to add 16 and 24 together, and our answer is 40. Now, what about when you have objects that repeat? Consider the number of 4-letter arrangements using the letters from the word pool, P-O-O-L. So there's actually 24 of them that are written out there, but you can see that a bunch repeat. So on the screen, you can see that the O's have different colors. So you can see, right, which one is changing position and which one isn't. But even when we do that, all the arrangements on the bottom row are exactly the same as the arrangements on the top row. The only difference is that the color of the O's differ. Normally, it's not going to be color coded. So all the variations on the bottom are the same as the variations on the top. So the number of different arrangements would be half. We've got 4 letters there. If all the letters would be different, there'd be 4 factorial or 24 arrangements. But because there are 2 identical letters, 2 O's, if they were different, they could be arranged in 2 factorial or 2 ways. But the number of 4-letter arrangements possible when 2 of the letters are the same, which we know is going to be 12, can be found by going 4 factorial over 2 factorial. That's how we get our 12. Why do we need to divide by 2? Well, because there are 2 letters that are repeating. So a set of n objects with A of one kind that are identical, B of a second kind that are identical, and C of a third kind that are identical can be arranged in n factorial, because that's the total number of objects, divided by A factorial times B factorial times C factorial, etc. There's no limit to how many objects are being repeated. There's no limit to how many factors you can have on the bottom. So if we want to get the number of different 8-letter arrangements from the letters of the word aardvark, so there are 8 letters which can be arranged in 8 factorial ways, but we have repetition. There are 3 A's, so you have to divide by 3 factorial. There are also 2 R's, so you also have to divide by 2 factorial. So on the calculator, when we do this, I will put the 3 factorial and 2 factorial in brackets. And 2 factorial is just 2 times 1. But we put it in brackets to make sure that the 3 factorial and 2 factorial are both in the denominator. So we get an answer of 3,360. Again, repetition, when you switch the A's around, it doesn't look differently. It's the same arrangement. So we have to compensate for that. How many different 5-digit numbers can be made by arranging all the digits of 17171? So again, there are 5 things that are being arranged, but there's repetition. There are 3 1s and there are 2 7s. So we're going to divide 5 factorial by 3 factorial times 2 factorial. So I can go back to that previous one and just change the 8 to a 5. It's the same thing on the bottom. 10 different 5-digit numbers are possible. We can use this same process to deal with a question like number 6. How many paths or routes can you follow from A to B in a 4x6 grid if you may only move up or to the right? So no backtracking. So this can be done using repetition. What you have to remember with something like this is you don't start counting until you start moving. So if you're going from A to B, how many if we call these city blocks, how many blocks do you have to actually travel? Now remember, you don't start counting until you move. So from A, there's 1 block. 2, 3, 4, 5, 6, 7, 8, 9, 10. You're going to travel 10 blocks. And it doesn't matter which route you follow, in the end, it's going to be 10 blocks total. So that can be done in 10 factorial ways. However, once again, there is repetition. So remember, we don't start counting until we actually start moving. So if I count the number of blocks that go west to east, now, and again, you don't start counting until you start moving. So that would be the first street that you would count, moving west to east, because you don't start counting until you move. That'll be the second, the third, and the fourth. Okay? If you started at the bottom, then you wouldn't have to count that top one. So again, you don't start counting until you move. So this is repetition. There are four streets that go in the same direction, east or west to east. And what about the ones that go south to north? Again, you don't start counting until you move. So if I change the color starting at A, I wouldn't count the first one because we don't start counting until we move. That'll be the first one. And the second, third, fourth, fifth, and sixth. Those repetition involve going south to north. There are 6 that go in the same direction. So you can get this answer by going 10 factorial over 4 factorial by 6 factorial. And again, to do this, we're going to have to use brackets. Try that again. 10 factorial divided by, in brackets, 4 factorial times 6 factorial. So that gives us an answer of 210. And that's one way to do this. Now, as we work our way through this chapter, we're going to see 2 other ways that we can do these types of questions. They're known as pathway questions. How many paths can you follow? So one is thinking about it in terms of repetition, but like I said, we're going to learn 2 other ways that we can do these types of questions. But let's do some more examples with these permutations and restrictions. How many different 3-digit numbers can you make using the digits 1, 2, 3, 4, and 5 if repetition is not allowed? So this one, there are no restrictions. It doesn't have to be greater than a certain value. It doesn't have to be even or odd. So you're just arranging 5 objects, except you're not using all 5 of them. You're only going to use 3 of the 5. So using the fundamental counting principle would be one way to do it. There'd be 5 choices for the first, then 4, then 3. 5 times 4 is 20, times 3 is 60. That's one way to do it. Or another way to do it would be using permutations. 5p3. You've got 5 digits, you're only going to arrange 3 of them, and order matters. So that's another way to do that. So using the calculator, 5 math over to probability, 2 is my NPR function, 5p3 also equals 60. So 2 different ways that could be done. How does it change if repetition is allowed? How does the application of the fundamental counting principle in part A change if repetition is allowed? Determine how many 3-digit numbers can be formed that include repetition. So for B, it changes because the number of possibilities doesn't change. It's 5 times 5 times 5, which is 125. And you cannot use permutations for this, because if you use permutations, it means no repetition. Okay, repetition. If there's no repetition, you cannot use if there is repetition, you cannot use permutations. Can't. We saw last class how we use our factorial notation. Basically, you're using the NPR formula, which is on the formula sheet. It's n factorial over n minus r factorial. So we'll get 7 factorial over 5 factorial, which we can simplify without even touching a calculator, because 7 factorial is 7 times 6 times 5, and we go all the way down to 1 if we wanted. But we stop at the 5, and whatever factor we stop with, we put a factorial on the end, because that's the denominator. So they cancel, and you're left with 7 times 6, which is 42. Part B, show that 5 factorial minus 3 factorial is equivalent to 19 times 3 factorial. So we saw one like this last class. By working down the left side, 5 factorial is 5 times 4. And again, I could go all the way down to 1 if I wanted, but I'm going to stop at 3 and put a factorial on that because 3 factorial is the second term. There is a common factor of 3 factorial here. And you're left with 5 times 4 minus 1. If you divide both of those terms by 3 factorial, that's what you'll get. 5 times 4 is 20, and 20 minus 1 is 19. So there we've got the same thing on both sides. Doesn't matter that they're written in different orders. When you multiply two factors together, order doesn't matter. Right, so there's part B done. Part C, you're asked to solve for n. And again, there have been questions like this on diploma exams, only it'll say determine, which means you have to show your work. Because you can definitely use guess and check until you get the right value of n. But we need to do this algebraically by expanding NP2 using the NPR formula. And we can simplify by expanding the numerator. Remember, when you're deciding which one to expand, choose the bigger expression. N is bigger than n minus 2. So you're going to get n bracket n minus 1, and we could keep going forever, but we're going to stop at the n minus 2 and put a factorial on it because that's our denominator. They will cancel. So we have a quadratic here that we need to solve by making it equal to 0. And then factoring. It'll be n minus 8, n plus 7. And as we saw last class as well, n cannot be negative because n refers to the number of objects you're choosing from. You can't have a negative number of objects to choose from. So n must be 8, and we can check that. If we go np2 and let n equal 8, 8p2 should equal 56. And it does. So it checks. Okay? How many ways can one French poster, two math posters, and three science posters be arranged in a row on a wall if the two math posters must be together on an end? So you've got a total of 6 posters here altogether. And what you have to realize here that there are 2 possibilities that we need to look at. The first possibility would be if the math posters are at the left end, or the first 2 positions. The other possibility is if they are in the last 2 positions. They just have to be on an end. Can be on the left end or the right end. So there's 2 factorial ways that the math posters can be arranged amongst themselves. Times, you have 4 remaining posters that can be arranged in any order, so that could be in 4 factorial ways. Remember, or means plus. This next one will be 4 factorial times 2 factorial, which is the same as 2 factorial times 4 factorial. So either way, it's 2 times 4 factorial, which is 48. 48 plus 48 gives us an answer of 96. So there's the answer to part A. What if the 3 science posters must be together? So remember, that means if one moves, the other must move with it. They count as one object to be arranged. So that one object plus the remaining 3 posters gives us 4 objects to arrange. They can be done in 4 factorial ways, but we also have to multiply by 3 factorial. What does that 3 factorial represent? Why are we multiplying by 3 factorial? No. We've already dealt with the 3 that are left by adding that to the 1 object. The 3 science posters. They can be arranged amongst themselves in 3 factorial ways. That's where the 3 factorial comes in. So 4 factorial times 3 factorial, which is just 6, gives us 144. Part C, what if they cannot be together? So probably the easiest way to do this would be all possibilities minus the possibilities with the science posters together. There are 6 posters there, so all possibilities would be 6 factorial minus those with the science posters together, we already know, is 144. So 6 factorial minus 144 is 576. Now, we did an example before where Reese and Caddison, or was it Shea and Caddison, couldn't sit together. And I showed you 2 different ways to do that. And the second way wasn't too terribly complicated. But doing this one the second way would be a lot more complicated. And here's why. Because you have 3 that cannot be together, which means you can have them all 3 separate, or you could have 2 together and the other one not together with them. So it would be a lot more complicated to do the second solution, like we did the earlier one. So the second solution, you'd have to do 2 different scenarios. You'd have to do all science apart, plus the second scenario with 2 science together and the other one apart. So you'd have to do that step with marking down the spaces, the different size spaces, or different level spaces. You'd have to do that twice and then add them together. It would work, but it's just a lot more complicated than the way we actually did it. Okay? And I mean, I can show you what that would look like, but it's so much easier to do it the other way. But that's what it would involve. So we've already talked about ones like this, arrangements requiring cases. To solve some problems, you must count the different arrangements. In cases, for example, you might need to determine the number of arrangements of 4 girls and 3 boys in a row of 7 seats if the ends of the rows must be either both female or both male. And so again, these are scenarios where you would take the 2 cases and you would add them together because it's one or the other. So we've done ones like that before. How many 4-digit odd numbers can you make using digits 1 to 7 if the numbers must be less than 6,000 and no digits are repeated? Again, we've looked at ones like this before, because we're going to have to look at 2 scenarios. The first scenario would be if the first digit is even, or if the first digit is odd. Because if the first digit is odd, it's going to affect how many choices we have for the last digit. The 4-digit number has to be odd, which means the last digit must be odd. And if we choose a odd first digit, that's going to affect how many choices we'll have for the last digit. But if we choose an even first digit, then it doesn't take that restriction, or it doesn't affect how many choices we have for the last one. What's different also about this one compared to the one we did before is this one has 4 digits, where I think the other one we did was a 3-digit number. Also, the digit has to be less than 6,000. So that means the first digit cannot be greater than 5. It can be a 1, 2, 3, 4, or 5, right? But this first scenario means the first digit has to be even. So now it can either be the 2 or the 4. There's 2 choices for it. And this doesn't limit how many choices we have for the last digit. Because our number has to be odd, the last digit has to be odd. It can be a 1, a 3, a 5, or a 7. There are 4 choices for the last digit. We started with 7, we've used 2. That leaves us with 5 times 4 for the remaining 2 spots. So 2 times 5 is 10, 4 times 4 is 16, 10 times 16, 160. Plus, if the first digit is odd, and again remember it has to be a number less than 600, that means it can be a 1, a 3, or a 5. There are 3 choices there. And because the first digit is odd, that leaves us only with 3 choices for the last digit. The number has to be odd, so the last digit has to be odd. We've already used 1 for the first digit though. So again, we started with 7 digits. We've used 2. There's 5 times 4 left for the remaining. So here, 5 times 4 is 20, times 6 is 120. Oh, 20 times 9, excuse me, should be 180. 3 times 3 is 9. And 160 plus 180 gives us 340 altogether. Okay? So next week we'll start looking at combinations when order doesn't matter. Yes?
For the first digit even, why did you put 4 twice?
So if the first digit is even, there are 4 choices for the last digit. The number has to be odd, so the last digit has to be odd. That means it can be a 1, a 3, a 5, or a 7. 4 choices. Good, good? So question 8 and 10 through 15. I will put these answers on Google Classroom so you can check your answers. Okay?